This is CalcPath Geometry, Lesson 1.6, Solving Systems of Equations and Inequalities. And we're going to be focusing in this video clip on learning target 4. At this point, we've already discussed what a system of equations is, that the system of equations is two or more equations with at least two variables, and that's the type that we're solving, two equations, two variables, where the solution is a point that makes both equations true. And we've seen so far in Learning Target 1 how to solve the system by graphing, and we also looked at how to solve a system of inequalities. But today our focus is Learning Target 4, solving by elimination. Before we jump to, actually it would be better for you to flip backwards. The very last page has letter D, and you can see Learning Target 5, and you're going to flip backwards till you see Learning Target 4, solving each system using elimination. We have several examples to go over, but before we get to those, I would like us to go over just some basic things. Elimination, the whole goal of elimination, and you don't need to write this down, but our goal is for us to simplify this system by trying to eliminate one of the variables to make it so that it's more like problems we've solved before, like 3x equals 12. Okay? So if we can get it to something simple where we only have one variable, then we can find the answer to that variable. So here's the idea. We have expressions like 2x or 17y, and our goal is to try to make them get eliminated, okay, through a series of multiplication and addition. This is also called multiplication and addition method. What is the opposite of 2x? You should know that that's negative 2x, right? So that's negative 2x. The opposite of 17y is negative 17y. Well, when we're looking at equations, our goal is to get some of these variables to be opposites. Now in the first two examples, we already have that. But we're going to be doing this through multiplication. So before we jump into this, I want to look at if I had an equation like 2x, or if I had an expression of 12x and my other one was 3x, what would I need to multiply this expression by to make these opposites? To make these opposites, I'd have to multiply by negative 4. So if I did that, then this would become negative 12x, and up here I would still have 12x. When you add them together, they would become 0. 12x minus 12x is 0. So that's the elimination piece of it, eliminating a variable by adding these things together, by adding the opposites together. But it's a little bit different. We're putting this idea together of eliminating a variable along with solving an equation, or solving a system of equations. So when I have this, I'm not just going to have this, I'm going to have an entire equation like 3x plus 2y equals 10. And my top equation may have been 12x plus 6y equals 20. I'm not sure. We'll make this a 20y down here. You're not writing this down, you're just following along. The idea here being that, yeah, you want those to be opposites, great, they're going to cancel out when you add them together. But now we're going to be doing this with equations. We have one linear equation here. I could find its x and y intercept if I wanted to, or put it in slope-intercept form, but that's not what I'm doing. I'm not supposed to be graphing it, and it would be fractional anyhow. I have another linear equation here, and supposedly they intersect at some point. We want to try to figure out the x and y coordinates, or the coordinates of the xy point that make both these equations true. Using elimination, we're going to do the same thing. Hey, look, I know that if I multiply 3x by negative 4, then I'm going to get the opposite of 12x. The problem is, though, when you multiply, I can't just multiply this or the equation changes. This is 3x plus 2 or 20y equals 10. If I multiply it by negative 4, I have to multiply every single term in the equation by negative 4, giving us negative 12x minus 80y equals, don't forget to multiply it over here, negative 40. I have now changed the equation, but it's still balanced because every term was multiplied by negative 4, or rather both sides of the equation were multiplied by negative 4. So it's still balanced. So with this, I have an expression like this. So that's the multiplication. This is the addition part of what they call the multiplication addition method, or for short, we call it elimination. Oh, that was going to be a negative 40. Better make sure I put the correct sign. So I'm copying. No, I didn't copy it down right. This is minus 80. Good thing you're not writing this down yet because it's not our actual example. So by multiplying that through, these became opposites. When I add vertically, I'm adding the two equations together. This one becomes 0. This becomes 86y, and this becomes negative 20. And yes, we are going to get a fraction for y on this system that I set up, but we would be able to solve for y if we were looking at this. Just giving you a little bit of preview of what we're going to be doing in this lesson. So to solve by elimination, our goal, we're going to target a variable to eliminate That's our first step. Our second step is going to be to figure out what to multiply by. Use multiplications, or use multiplication. We're going to use multiplication to make the coefficients opposites. So the first two steps, target a variable to eliminate and to use multiplication to make coefficients opposites. In the first two examples, there will be more steps to this. In the first two examples, this is already done for us. If you look at this, yes, I could target x. If I were doing that, I'd multiply this entire equation by negative 3. But I don't need to do that step because if I look carefully, my y's are already opposites. So now I can use the addition method. So if I add these two equations together, this gives me 4x. The y's are eliminated, so there is 0y. And 10 plus negative 2 is 8. So I have 4x equals 8. Just using this is the addition part of elimination. Now I can solve this for x. Since 4x equals 8, if I divide both sides by 4, x equals 2. But that's not my complete solution because we know that a solution to a system of equations is an ordered pair x comma y, a point, an x value and a y value that make both equations true. So even though I know that my answer is 2 for these, I need to find out what value of y works. And I need to check my answer as well. So I'm basically going to plug 2 into both equations and make sure that I get the same answers for y. So if I know the answer for x is 2, I can write out 3 times 2 minus 4y equals 10, and 2 plus 4y equals negative 2. I'm just going to be plugging in the 2 into those equations. I know the answer to x is 2, so we're plugging it in. That makes this 6. So this equation right here becomes 6 minus 4y equals 10. And I'm going to solve that one over here. I'm going to subtract 6 from both sides. I have negative 4y equals 4. Divide by negative 4. I get y equals negative 1. Now I'm going to do the same thing on the other side of the equation. This is already simplified. To get y by itself, I'm going to subtract 2 from both sides. That makes this 4y equals negative 4. When I divide both sides by 4, I once again get y equals negative 1. So I know that when x is 2, y is -1 for both of these. Thinking about the graph, I have two graphs. One has a positive slope and one has a negative slope. If you look at the equations, you can tell, remember, it's the opposite of x over y, the opposite of x over y. And where they intersect, that is at x matches up to 2, and the height there is -1. The height of the graph is -1. So our point is 2, -1. And we did this without graphing, though, because we're supposed to be using the method called elimination. For our next problem, we once again look at the variables, and we see if we're going to target a variable. We're going to look and see which one's easiest to eliminate. The good part is this one is already set up to eliminate. If I were targeting y, if you said, oh, look, y is easy to multiply because that's a 2, I can multiply this whole equation by -2. You could do that, it would work, and I'll show you how to do that with some problems in a second. But we don't need to target the y, it's easier to target the x because they are already opposites. Already opposites. So that helps. So now we can move to adding the equations. By the way, when we're going to target these, when we go to use elimination, you can do it in other forms, but the preferred method is to have the equations in standard form. If they are not both in standard form, if one of them's in standard form and the other one isn't, you need to get them into standard form to line them up like this. So your x's are lined up, your y's are lined up, and your constants, the number on the other side of the equal sign, are lined up. And if they're not, then you need to put them in standard form first. So for this, we have this system, and luckily these are opposites. So when I add the two vertically, this becomes 0. This becomes positive 3y. -2 plus 14 becomes 12. So now I can actually solve for y by dividing both sides by 3. Y equals 4. I'm going to write my ordered pair for my answer and put y as 4. I still have to figure out what the x is. To do this, I'm going to rewrite these equations. Really, I only need to do one, but we're doing both to make sure we didn't make any mistakes, to make sure that we get the same answer for both of them. 3x plus y equals -2. And the other one is -3x plus 2y equals 14. So I'm going to take my 4 for y, and I'm going to plug it in. And now I should get the same answer for both x's. Here I'm going to take away 4 from both sides. That leaves me with 3x equals -6. When I divide both sides by 3, I get x equals -2. So I think that's my answer for x, but I'm going to check it by plugging into the second equation to check. So I have -3x plus 8 equals 14. I'm going to subtract 8 from both sides. That gives me -3x equals -6. Oh no, equals +6, so we're okay. And when I divide both sides by -3, I get x equals -2 again. So I know that y was 4, that's correct, and that when I plugged it in, I got the same answer for both x's. So the solution to this particular system right here is -2, 4. If we were to graph these, either using x and y intercepts, for these two lines, they would intersect at the point -2, 4. That is the values of x and y that make both equations true. In our next example, we have variables that are not lined up. If you look carefully at this, the top equation is in standard form and the bottom equation is not in standard form. And so what I'm going to do is draw an arrow over. The top one just stays the same. It's going to be 2x plus y equals -5. The bottom one, I really need to add 2x to the other side to get the constant by itself and to get my x and y on the same side. In doing that, this gives me 2x minus 5y equals 13. So since I added to both sides, the equation, even though it looks different, it's still the same equation. I just moved the 2x over to the other side. So as I go to solve this problem, I'm looking for a variable to target. Now some people said, oh, target the y. There's only a 1 there. You could multiply this top equation by 5. That is, in fact, what I'm going to do this time to show you that. However, there are some people who said, well, look, the x's are the same number, and I want them to be opposite. So if I just multiply one of them, maybe the top equation or the bottom equation, either one should work, by a -1, and I distribute it to every term, then these would be opposites, and we can do what we've done above. Well, I'm going to target y. My target is y. So since this is -5y, I need this to be +5y. So I'm going to have to multiply my top equation, every single term in it, by 5. In doing that, and I'm just going to write it off to the side, hopefully you have some room over here, this becomes, and that's a +5y that I'm multiplying by, 10x plus 5y, and don't forget to distribute to every single term in the equation, even the other side. 5 times -5 is -25. It's actually one of the most common errors is people get the right number they're supposed to multiply by, but they only do it to one side. The equation will no longer be balanced if this were still a -5 over here. We have to multiply every term by 5. And then my other equation is exactly what I want it to be, so I just copy that back down. It is 2x minus 5y equals 13. Well, now that I've taken these equations, the first thing we did was put them in standard form. Now we targeted y, and we got the y's to be opposite values. So now I can add the two equations together. And you don't have to target y. You could have targeted x, but I chose to target y. This gives me 12x, the 5y and the -5y are eliminated, equals -25 plus 13. So I've been, here we go, 13 plus -25, -12. And so when we divide both sides by 12, we get x equals -1. And that's our answer for x. So for this original system, I go back to my original system, this one right here, we have a solution of x equaling -1, and we have to figure out what the y is. So I'm going to do that, and I'm going to do it in both equations. Since my x is -1, this top equation becomes 2 times -1 plus y equals -5. I'm just plugging it back in. Wherever I see an x, I know x is -1, I'm making it what it is. And so when I do this one, I have -2 plus y equals -5. I add 2 to both sides, and I get y equals -3. I'm going to verify that this is actually true by plugging the x into this equation. You could also plug in both the x and y to see if it's balanced, but I'm just going to plug in the x and solve. So when I plug in the x, I have -5y equals 13 minus 2 times -1. That's me plugging the -1 into the second equation. This is -5y equals 13 plus 2, which 13 plus 2 is 15. And when I divide by -5, y is -3, just like I got here. So I know that this is the correct answer for the y for both equations, and that those occur when the x is -1. So there's the answer to that system. Now in this case and in the previous case, it worked out really nicely that, well, this one wasn't lined up, but it worked out really nicely that I only had to multiply the top. And in the previous two cases, I didn't even have to multiply. They were already opposites. Okay? This brings us back to what we've been doing on all three of these. We targeted a variable to eliminate. On the one we just did, we had to use multiplication to make the coefficients opposites. Step 3, and you may need to find room somewhere on here, or if you keep a separate journal for steps. 1 second. So now that the school's music is done playing, target a variable to eliminate. Use multiplication to make coefficients opposites, which we just had to do for the first time in this case. Step number 3 is to add the equations vertically together, add them together vertically. From there, the next step is to solve for the remaining variable. And then lastly, we take the answer that we got and we plug it back into the original system to solve for the other variable. So plug answer into the original equations plural, because we want to make sure that our answer is right, to find the other variable. When we plug something in, plugging an answer in, that's actually called substitution, which is another method that we're going to learn. Right now we're focused on elimination. All right, so let's look at the next example. There's only 2 more examples on this. 5x plus 2y equals negative 11, and 3x plus 6y equals 3. So on this particular example that we're looking at, neither the x nor the y are opposites. We are lucky in that the equation is already in standard form, so that's helpful. But the x's are not opposites, the y's are not opposites on their coefficients. And honestly, I could pick either one for this one. If this were just a 1y, then I would just multiply this whole equation by negative 6, since I already have the positive 6 coefficient down here. But it's a 2y, so at this point, I need to figure out what I'm going to multiply by. And so I need to find the least common multiple of either the y coefficients or the x coefficients. And it doesn't really matter which, they should both lead me to the same answer. For this problem, I am going to target the x coefficients. The least common multiple of 3 and 15, or sorry, I just said it, 3 and 5 is 15. So I know that ideally I want this to be, I want my top one to be a positive 15x, and I want my bottom one to be a negative 15x. That's what I really want, so that these can be opposites and get eliminated when I add the equations together. So in order to make this a positive 15x, I'd have to multiply this entire top equation by 3. And I'm going to do that in just a second. And in order to make sure that the bottom equation is becomes negative 15x, I'd have to multiply the entire bottom equation by negative 5. 3 times 5 is 15. Negative 5 times 3 is negative 15. They're going to become opposites, those coefficients, and that's the goal. That's what we're trying to do in step 2. So now that I know the numbers I need to multiply, I just need to distribute. I have 3 times 5x, that is 15x. 3 times 2y, that is 6y. And 3 times negative 11, that is negative 33. So I've changed the top equation. It's still balanced because every term was multiplied by the same number, or the left and the right were both multiplied by 3. On my bottom equation, I'm going to distribute the negative 5. So negative 5 times 3x is negative 15x. Negative 5 times 6y is negative 30y. And negative 5 times 3 is negative 15. Now that I've gotten these to be opposites, step 3 is to add the equations together vertically. So when I add these two equations together, my x variables are eliminated. I end up with negative 24y equals negative 48. To solve for y, I will divide both sides by negative 24. And I get y equals 2. This means that my solution is something for x, we're not sure what yet, comma 2. Because we now know that the answer for the y variable for both these equations, the point where they intersect, is 2. To find the x, I'm going to plug this 2 back into these original equations. My original equations were 5x plus 2y equals negative 11. And the other one I'll write in a second. So I'm going to put the 2 in here. That makes that 4. 5x plus 4 equals negative 11. I'm going to subtract 4 from both sides. 5x equals negative 15. Divide both sides by 5. I get x equals negative 3. Now, it's nice when they turn out to be whole numbers, but it is possible for them to be fractions. We just want to make sure that the other side's also going to, or the other equation, this one, is also going to be x equals negative 3 when y is 2. You could plug this in if you want. I've got 3x plus 6y equals 3. Well, we already know from what we just solved, we think our x is negative 3. And we've solved originally for our y to be 2. Now I don't have to solve anything, I just plug it in. This is negative 9 plus 12 equals 3, which it does. So I know my answer is correct. That when y is 2, x is negative 3. And when x is negative 3, y is 2 for both of my original equations and every equation in this system. Last physical example, and then I'll have a second clip for those of you who want to try one or two problems. So with this problem, we don't have them in standard form, which is a little bit of a problem. So I'm going to subtract 7y from both sides on my top equation so that my x and y are on the same side and my constant is by itself. On my bottom equation, they are already in standard form, so that's helpful. All right. Now, I'm going to target, doesn't really matter what I target, I'm going to target my x's. And unfortunately, 2 doesn't go into 7. Their least common multiple is 14. Since the least common multiple is 14, I'm going to need to multiply my top equation by 2 to make this a 14x. And to get its opposite value, negative 14x, I'm going to have to multiply my bottom equation by negative 7. Because negative 7 times 2x is negative 14x. Doing this will make sure that my coefficients on my x are opposite. So I'm going to distribute the 2 to the 7x. That gives me positive 14x. To the negative 7x, it gives me negative 17 or negative 14y. And to the 14, which gives me 28. When I do this on the bottom, I'm going to distribute my 7, which gives me my negative 7, which gives me negative 14x, my negative 7 to the negative 2y, which gives me positive 14y, and my negative 7 to the positive 4. This gives me negative 28. When I add these two equations together, the x's cancel just like I expect. But so do the y's, leaving 0 on the left-hand side, and so do the 28's, leaving 0 on the right-hand side. So what does this mean? What this means, 0 equals 0, the equation's still balanced, so most of you know that this is infinite solutions. This is many solutions or infinite solutions. What does it mean in terms of our graph? Well, You might have encountered this when you were graphing problems, but our equations started as, well, we had 7x minus 7y equals 14, and 2x minus 2y equals 4. Watch what happens if I do notice that 7 goes into all of these. If I divide every term by 7, okay, equation's still balanced. I did that to every term. I get 1x minus y equals 2. And then I notice on this equation, hey, look, all of those numbers are divisible by 2. So I divide it by 2. I get x minus y equals 2 again. So it's infinite solutions because they are the same equation. And since they're the same equation, when I do go to graph this, which it's going to have a negative slope, I'm not actually going to graph it. I graph the one line, I graph the other line right on top of it since they're the same equation. Every single point that's on this line is also on this line. So every single point on this line is a solution. And since there are infinitely many points extending this direction and this direction, and even between these, that is why it is infinite solutions. Had we solved this same system, or not the same system, but a system like this, and had both variables cancel out again, and instead of 0, 0, we had 0 equals 42, and let's say one of these wasn't 28, then this would be no solution. And what this would mean in terms of the graph is something we'll talk about later. At this point, all the examples have been covered for learning target 4, being able to solve systems of equations using elimination. There is a second video clip for you to be able to check the answers to at least 2 try-it problems. So I would ask you to try letters A and B, and if you're plugging them in and it's not working out, then you will want to watch the next clip. Have a great day.